Hello, everybody. My name is Ben Russell, and today I am presenting my research that I've been working on for the past 2.5 months over the summer. My research topic is the mathematical model of the co-infection of COVID-19 and pneumonia and the transmission dynamics between them. So a little outline before, we're going to look at the background, the model itself, some numerical simulations, and then conclusions, and we'll be done. So quick little background for COVID-19, even though probably don't really need one, but COVID-19 is a coronavirus disease type, which means that it spreads through air droplets and small airborne particles, which makes it a respiratory infection very similar to pneumonia. It's going to attack the lungs and whatnot. So that's what we're really interested in, is that since pneumonia and COVID are very similar in how they infect and how they attack, we want to see what happens with a similar type of hosts. We haven't seen a lot of research done into the codynamics of pneumonia and COVID in general. We've seen a lot with HIV and malaria and other types of large diseases, but there are no carriers, and it's just air droplets. So we're going to model this by using an SIR model, which is a compartmental model, and it's a variation of SIR model. An SIR model is susceptible, infectious, and recovered. So we're going to see how the population is affected by infectious people. So in our case, we're going to look at susceptible people, and these susceptible people are going to interact with infected people. And these infected people are going to eventually recover after a certain amount of time. And that's how we're going to model it. We're going to put this just in a couple of boxes, and then there's going to be a rate that they go through these boxes. You can actually add on to it, however, like in the bottom right corner, we can see all the different types of models that we can create, which doesn't include ours, but I'll just show ours relatively soon. So we can do so many different types of things with SIR models that we can accurately describe how COVID and pneumonia is going through our population. So our model is very similar. Like I said, it's an SIR model, but it is actually an SVIRD model, where the V stands for vaccination and the D is for death. So our death compartment isn't terribly interesting because all it does is accumulates deaths from pneumonia and COVID. Our vaccinations is just how many people get the vaccines from COVID and pneumonia. There is a pneumonia vaccine, which is kind of crazy. I didn't realize that there was one, but there is. And so also there's going to be a co-vaccination one, which will be very, very small amount, which we'll see when we see the numerical simulations. Our actual model is going to be based off of these 9 differential equations. These 9 differential equations are going to show us how people move through the compartments. So I want to quickly go through DSDT to show you kind of how it works. So it's going to be our topmost differential equation. So our gamma R is going to be how many people come back from recovered after their immunity has waned. Our lambda is how many people are born into our system. Our S is susceptible, obviously, and then that big term is going to be all of the interactions. So the interaction, there's the rate of people getting vaccinated for pneumonia, COVID, and both. Then there's going to be a interaction between susceptible and the infected for pneumonia, COVID, and both. And then depending on which one it is, we're going to have a contact rate to see, while only about 40% of the time do people in those interactions actually get COVID. And so we're also going to see a natural death as well. That's for dynamics. The birth and death rate is going to add people into the system and people leave and have people exit the system. So that's what we see with these differential equations. But we can do a lot with these differential equations so that we can prove that it's that this is what is actually happening in our life. So we're going to quickly look at COVID, though, because if we look at the co-infection, that's a lot of stuff all at once. So we're going to look at COVID first to minimize the amount of stuff that we have to do, and then translate that to our larger co-infection model. So the first thing we do is find the equilibrium points. So the disease-free equilibrium is just when there's no COVID. When there's no disease present, that is the equilibrium point. Our equilibrium point is when we set all of our differential equations to 0, and then we solve. Our endemic equilibrium point is when there is COVID, but it's when our obviously all of our differential equations are set to 0, so they are set in stone. And that IC star, we're just going to prove its existence because it's very, very difficult to do. If you would like to see the proof or the proof of its existence, please let me know. It's just too much to put in this right now. But please contact me if you would like to hear about it. So our reproduction number is something that comes out of all this. Our reproduction number is how many people one person infects because of how many people one person infects with the disease. And so the more people is an epidemic. Obviously, if you're greater than 1, you're going to create an epidemic. More people are going to get infected because of you, and it's going to constantly grow. An endemic is just constantly, there will always be one. So an endemic will be, our reproduction number would be 1. However, what we're really interested in is what happens if it's less than 1, especially at the disease-free equilibrium. Because if the disease-free equilibrium is less than 1, then we know that our system is working. So we're going to look at the local stability. The local stability is going to show us that our reproduction number works. And we're going to see and make sure that our model works in general. So in this case, we're going to take the determinant of a characteristic matrix, and we're going to find some eigenvalues. So these eigenvalues are going to show us some stability. And the one that we really, really care about is the third one, because it's going to give us, because if we do a little bit of algebra, we'll see that R naught minus 1 is what we end up getting out of that third one, which means that if our reproduction number is less than 1, the disease-free equilibrium is locally stable, which makes sense because there shouldn't be more people getting infected based off of how many, there shouldn't be any people getting infected when there's no COVID in general. So the other issue is our endemic equilibrium is a little bit trickier, and I'll touch up on that at the very end. So stay tuned for that. And also in the very bottom right, because it's kind of difficult to understand the stability, but imagine if you had an XY plane and you had a point in the middle. Now, all of those arrows are going to circulate around this, this specific point and it'll be an equilibrium point. And now, based off of what that flow is doing, it will be either stable or unstable. There's also some other stuff that happens in dynamical systems, but we're really just curious about unstable and stable points. So if we're going to look at, we need to look at more equilibrium points because we need to look at our coinfection model. Our coinfection model is going to have 8 dimensions. Our COVID-only model only had 4, which is really easy, but our total pneumonia and COVID model is going to have 8. And we're going to see that in the endemic equilibrium, we're going to have just COVID. We're going to have for 1 and 2, we're going to have COVID only and then pneumonia only. And then obviously the disease-free equilibrium is when there's none. So we're going to quickly look at the disease-free equilibrium because that's what that one is the easiest to do. And we can find that after doing, again, the same process that we did for COVID, we can find that based off of just the 5th and 6th eigenvalues, those are going to determine whether it's locally stable. We get the bottom terms from our eigenvalue. And what we end up finding is that those are just the reproduction numbers. Those reproduction numbers are going to be found from another process. And what we can find from this is that, again, as long as the reproduction number is less than 1, our disease-free equilibrium is stable, which is really, really important for determining that our model actually works. So now we're going to look actually at some numerical simulations. The numerical simulations are important because this is our actual data. We're going to compare this to real life meaning. This is what it looks like just when you run the MATLAB code, this is what you get. And it's a little bit difficult to look at, so we're going to go piece by piece. So the first thing is our vaccinations. So vaccinations is a good way of explaining how the system works in general, because so people are vaccinated for COVID, but in our model, there isn't just a little tag that says vaccinated for COVID. No, they go from susceptible to vaccinated, but then vaccinated to infected, because if they're vaccinated, that doesn't necessarily mean that they're going to stay in that box forever. They're going to go out because they aren't completely immune from the disease. And we're going to see that for also pneumonia, because obviously pneumonia goes down and it kind of stables out at the very end. So same with the COVID vaccine. But we're going to see that and how it is with other parts of it as well. But it also makes sense that COVID is going to be much more vaccinated than pneumonia, because most people don't really even know that there is a pneumonia vaccine. Infections aren't terribly interesting to look at, other than because it's just that these are all the infections. We do see, however, that pneumonia tends to kind of goes very, very, very low. And COVID ends up being much more of an endemic than the pneumonia, which probably is presumptuous to there being the same host and COVID being much more infectious. Deaths are also very accurate. The amount of deaths that were predicted by our model is almost 5,000 away from what was actually done in the United States, which our model is based off of United States data, because that is what's most easily available to me. And there is a whole lot of it on the CDC website. Our coinfection is also going to be relatively important, because we're going to get a very small amount of coinfection, and it shows that comparatively, ratio-wise, that we're going to see a lot less coinfection than we're going to see regular infection. So lastly, we have susceptible and recovered. We see that the amount of susceptible people goes down, and that makes sense, because those are people that have never gotten COVID or get back into the recovered. And there aren't going to be a whole lot of people that never get COVID or recover, and it takes a very long time for them to be recovered, because obviously it takes about 6 months to lose that natural immunity. So a couple conclusions that we can derive. The model works. It works exactly how we thought it was. And it's very good at predicting how things are going to work, like how pneumonia and COVID-19 compete for each of the hosts. COVID ends up being much more of an endemic than pneumonia. What we can look at, though, is we can look at preventative measures to preventing future disease pandemics and endemics or epidemics from happening, or from being so detrimental to society. But for me to do that, I need to do a couple of steps first. There's a bunch of math that we need. The first 3 things are just a lot of algebra that I'd have to sit down and write through. And that would be the first step, is just more time to do all the algebra. The second part is just run more numerical simulations. That's all I would have to do, is just run more numerical simulations with different parameters and see how our model reacts to different things. And the last thing is we'd finally get to look at the preventive measures. We'd see how each of these things work. And we could give suggestions for preventing those future pandemics. So I'd like to thank the College of Science for giving me the opportunity to do this, for funding my grant. And thank you for Dr. Aganyagi for giving me the opportunity for research. Thank you.